So where did we leave off last time? So recall. What did we do last time? Right, so F, we had a definition of holomorphicity. F from some open neighborhood, so this is some open neighborhood, is called holomorphic if what? Let's say holomorphic at Z.
If the derivative at Z exists.
Right. If f of Z plus H minus f of Z over H has a limit as H goes to 0 in the complex numbers exists. Okay? And if it does, then we define that to be f prime at Z. And it's holomorphic, on omega if this is true for all Z in omega. Okay? Omega is some open set. And we proved, theorem, if F we can write as real part plus imaginary part is holomorphic, then what did we prove? We proved that you can evaluate the derivative by just taking the partial in the x direction, meaning u sub x plus I v sub x. We also proved that this is equal to, did we prove that this is equal to d dz of f? No. Okay, so let's make this a little mini exercise. If we didn't prove it, where, not to be hinted in, where, how did we computed ddz bar, ddz, which was as a formal operator. What was it?
One half d dx plus 1 by I d dy.
Right. So there's a half d dx plus 1 over I d dy. That's the, some people write minus I. I prefer to write it as plus because then d dz bar, you just have to remember that it's in the denominator. D dx minus 1 over I d dy. Otherwise, I mean, obviously 1 over I is negative I. But, you know, I just prefer to write it this way. So that the plus sign comes with Z. Whoops, I shouldn't make that look like a plus or minus. The plus sign comes with Z, and the plus sign comes with Z, and the minus sign comes with Z bar. But it's 1 over I. Okay. What else did we prove? We proved that the Jacobian, and if J sub F is the Jacobian, then the determinant of J is none other than anybody? Let's see, if you've already spoken, let's say if you've spoken twice, then raise your hand if you know the answer instead of just shouting it out. Remember we computed the determinant? Okay, so Sriram knows. What did we compute the determinant was? Ishan knows. Anybody remember? Okay, Nick, go ahead.
Du dx, du dy, dv dx, dv dy. Was those partials of u and v?
Right, it was the partials. It was like the partials, partial with respect to x. Well,
oh, you have to determine it.
I was looking for the most compact way, which is just, it's the derivative, absolute value squared.
Okay.
There's a variety of ways of writing that as, well, in particular in terms of, you could say ux squared plus vx squared. Or any other combination that comes from Cauchy-Riemann. We also proved Cauchy-Riemann. And so these are all consequences of holomorphicity. Okay, maybe this is consequence 1, that the derivative is the partial with respect to x. It's also the partial. And 2, the Jacobian can be computed in this way. And 3, the Cauchy-Riemann equations, CR is Cauchy-Riemann, which say, altogether, you remember what Cauchy-Riemann says? Who can I pick on? Anna, can I pick on you? You're the next person in my Zoom range.
Sure. So in the context of the partials, you have du dx equals dv dy. And then you have du dy equals negative dv dx.
Perfect. Right, so this Jacobian looks like a, b, negative b. And that's where this came from. What else? And one more thing, and one more consequence that we discussed was that d dz bar of f is equal to, you can all hold it up. Thanks, Thomas. 0. Okay, so these were some elementary things about, well, they're the Cauchy-Riemann equations and their various guises. Let's get a little practice with using these in applications. Okay, can you guys see all this? Any questions on this? No. All right, example 1. Sorry?
I think you meant dx on part 3.
Thank you.
Part 3, equation 2, dx.
Vx, thanks. Yeah, it's the off diagonals. So u is the real part with respect to the imaginary part. V is the imaginary part differentiated with respect to the real part. Thanks. Okay, example. Let's do example 1. I'm going to write f as v comma u, or v, you know what I mean by this, u plus iv. This is a u comma v rather, where u is equal to x squared plus y squared, and v is equal to 2xy. Is this holomorphic? All right, take a minute and compute.
Did we prove that the Cauchy-Riemann equations are sufficient for a function to be holomorphic?
Not yet. That's the next thing. That's the next thing we're doing. This is the warm-up to that theorem. And there's a subtlety there. They're not exactly sufficient. I mean, they are if phrased in the right way, but the most naive way to phrase the converse fails. So give me a hand, give me a thumbs up when you have an answer for whether this function is holomorphic or not. Okay, Burchin, can I pick on you?
Yeah.
So what do you think?
It's not holomorphic because uy is not equal to minus vx.
So ux, you said vy?
Uy is not
uy
minus vx, which is
u sub y. Yeah, so differentiate this with respect to y, I get 2y.
yeah,
And
then
vx, I differentiate this with respect to x, and I get 2y, which is not negative uy. So that's why, Mitchell, I said we're not yet up to the converse. We can use the forward direction to rule out holomorphicity. Cauchy-Riemann equations are not satisfied, so it's the contrapositive. So definitely not holomorphic. Not holomorphic, no Cauchy-Riemann equations. Okay, great. How about let's do another example.
Can you repeat what you just said, why it's not holomorphic?
Yes. So what we proved, this theorem above says if a function is holomorphic, then the Cauchy-Riemann equations are true. So the contrapositive of that is if the Cauchy-Riemann equations are not satisfied, then it can't be holomorphic.
Professor?
Please.
So for holomorphic, is it sufficient, like if del f by del z bar is 0, then can we say it is holomorphic, right?
We're almost up to that. I have a few more examples I want to show you before we get to...
Like the example you took in the first class, e to the power minus 1 by z square. So
That's a good example.
It's a del f by del z bar is 0, but it's not holomorphic at, like, it's not even continuous at 0. Because
That's right. That's right. Away from
Is it
0,
be-
it's a perfectly holomorphic function. At 0, you have all kinds of problems. There's an even simpler version of that. We'll get to it. Okay, you guys want to get there, right? I had a couple more examples I wanted to go through slightly more. Let's go a little bit slower. You guys are all there. Everyone knows where I'm going. I guess I'm telegraphing it. Or it's just the natural thing. The natural question is, do the Cauchy-Riemann equations explain whether things are or aren't holomorphic? Let's do one more example. U is equal to x squared minus y squared, and v is equal to 2xy. Holomorphic or not? I see Nick. Nick's ready with his answer. Sriram's ready. Thomas is ready. Rishab is ready. Take your time. Ishan's ready. Does anybody know what this is as a function of z? We already heard from Nick. We didn't hear from you twice yet. My rule was you can answer questions twice, and then I want to skip around to new people. So go ahead, Nick. What's f of z?
Z squared.
Z squared, right? This is exactly z squared because it's x plus iy squared, which is x squared plus iy squared, which is minus y squared plus 2ixy.
And indeed, it is holomorphic.
And indeed, it is holomorphic, and it satisfies the Cauchy-Riemann equations. Okay? Polynomials are differentiable just like they are over the reals. Okay. How about this example? U is x squared minus y squared, and v is negative 2xy. So for this one, I want you to compute d dz bar and tell me what you get. Good guess, Nick. Do your calculation one more time. ddz is what you held up. So now give me a thumbs up when you think you have an answer. Okay. Ishan's got, Nick's got, Thomas has got. Take your time. I'm going to go slow. Hannah, was that a thumbs up? No, you were just holding your pen?
Yeah, I was just holding my pencil. I think I'm done though. I think
Okay.
I have it. But
What'd you get?
I might have screwed up, but I have 2x minus 2yi.
2x minus 2yi. Perfect. This is also known as 2z bar. And what is the function?
Is it z bar squared?
Z bar squared. Perfect. Who said that? Kayla?
Yeah.
Yep. Z bar squared. For exactly the same reason. All we did was we changed this plus sign to a minus sign. That made v negative. And the derivative with respect to z bar is what it should be. And if you had computed this with a plus sign, everything would cancel instead of doubling. Okay, so ddz of this thing, so this is anti-holomorphic. ddz is 0. we're not really going to talk much about anti-holomorphic functions. But I just want to plant that seed in your head. All right. One more example. One more example. Yeah, u is x squared plus y squared. V is 0. Compute d dz. Let's see how fast we can start, how quickly we can get, how, what's the word, nimble we can get at evaluating these things instantly. You should start seeing patterns in this thing. You shouldn't have to do any calculation anymore. But if you don't see it immediately, go ahead and do the calculation. Give me a thumbs up when you're done working. Nick, you really don't like things that aren't holomorphic. If you're done with that calculation, then give me d dz bar. If you're still working on d dz, keep working on it, but then give me a thumbs up. Rishabh's got it. Let's see, I haven't picked on Brandon yet. Brandon, should I pick on you? No. Michael, should I pick on you? You're muted.
I'm kind of lost.
Oh, okay.
At
Please
least
stop
not-
me if you're lost.
Well, I mean, I'm following sort of, but I'm not anywhere ahead of you.
Okay. Back me up. How about example 2? Were you happy with example 2?
Oh, yes.
Okay. And example 3?
Yes.
Great. Let's do example 4 together. You and me. All right. So d dz bar. Do you have any idea what function, if I tried to write f as a function of z, what function it would be that would give us x squared plus y squared and no imaginary?
I imagine it would be an absolute value.
Yeah, absolute value squared, right? Norm z squared.
Okay.
Which is z times z bar, right? This is x plus iy times x minus iy. It's a difference of squares, so that would exactly come out to x squared plus y squared. Does that make sense?
Yes. Okay, so since it's got a z bar, it's not going to be holomorphic.
Yeah, that's exactly the intuition I'm trying to develop, so that we can see. It's really some complicated functions that are simple functions of z will look very complicated as functions of u and v. So it's not immediately obvious just from looking at u and v whether this thing is or isn't holomorphic. But let's run with this for a second. If this really is z times z bar, then what should d dz be?
Z bar.
Yep, it should be z bar. And what should d dz bar be?
Z.
Z. So let's see if that's right. Okay. So Michael, d dz is, what's the formula for d dz?
A half of d dx of u plus iv plus 1 over I d by dy u plus iv.
Perfect. Okay, so let's compute this. So v is 0, that's easy. There's no v's. And let's keep the 1/2. What's the derivative of u with respect to x?
2x.
2x. And 1 over I. And what's the derivative of u with respect to y?
2y.
2y. So the 2's and the 1/2 cancel. And we get x plus 1 over I. 1 over I is the same as
minus I.
Minus I, y. Also known as
z bar.
Z bar. Okay, So if it seems like magic, I mean, it works precisely because we computed, I mean, all we did is we treated z and z bar as independent variables when we computed what ddz and what ddz bar should mean as differential operators. And I'm trying to impart the fact that that's a good definition for these differential operators because they're computing exactly what they're supposed to be computing if you can write f in terms of z and z bar. Does that make sense? Okay. Yeah. So Michael, now you're happy?
Yes, happier. I still have to look at it. But
okay.
Yes,
So if you, do this, compute this on your own. Okay, that's a good exercise. This will give you more, you know, you're gonna start to get quick at finding these kinds of patterns. All right, let's prove the converse. So the converse to the Cauchy-Riemann equations, as all of you converse theorem, if u and v are differentiable in the sense now of functions from R2, they're functions from R2 to R. So if they're R2 differentiable near z, then f is holomorphic at z. Okay? And of course, and satisfy the Cauchy-Riemann equations and Cauchy-Riemann.
Professor?
Please.
Does this imply that if we had f of z, then f of z is complex differentiable also? Like instead of u and v are R2 differentiable, are they same?
So let's see. So what do I mean by u and v are R2 differentiable? What does u is R2 differentiable? I mean in the same sense as we discussed before. So u of, let's say, z, let's call this x. So in a neighborhood of z, so this is x plus h1, comma, y plus h2. So if I'm thinking of h as h1 plus I h2, and h is small, then I should be able to approximate the value of u at a perturbation by the original value of u plus a 2x1 matrix instead of a 2x2 matrix. So there's a 2x1 matrix, or what is this, 1x2 or something, acting on h1, h2, plus little o of absolute value of h. Plus little o of absolute value of h. And what is that matrix? Mitchell?
The row vector of partials.
Exactly, the partials. U sub x, u sub y. So that's exactly the notion of R2 differentiability. Okay? And the same is true, same for V. So far, so good? So now let's look. So here's the proof. Look at f of z plus h minus f of z. F, of course, f, by f I mean u plus iv. So if you have two functions, there are two differentiable near z, and they satisfy the Cauchy-Riemann equations. These cross terms are negative, and the same terms are the, you know what I mean? You know what the Cauchy-Riemann equations are. Then the function you create by making u the real part and v the imaginary part is holomorphic. So let's see why that's true. What is this? This is u of z plus h minus u of z plus I times v of z plus h minus v of z. Just sticking in that f is u plus iv. This difference is exactly what's on this side. right? Everybody sees this? This difference is exactly this. So what do I get? Partial, now this product is very easy to compute. It's just u sub x at z times h1 plus u sub y at z times h2. U sub y times h2. Right? Everybody with me? Anybody lost? Anybody confused? No, you could probably finish the proof yourself, but let's just write this out. So this difference is just this part. So this difference is just this part. I have to remember that you can't see when I'm pointing unless I use the pointer. So I get u sub x times h1 plus u sub y times h2. That's that difference. Plus I times the same thing with v's. V sub x times h1 plus v sub y times h2. And what's left over is an error term which goes to 0 faster than h goes to 0. Who's with me? Who's against me? Okay, Ishan, go ahead. No, you're just messing around. Okay. Well, gosh, this doesn't look very much like some function times h, but we haven't used. What are we going to use now?
The Cauchy-Riemann equations.
Awesome, Kayla. Cauchy-Riemann equations. So, Kayla, which ones do you want to mess with?
Ux and uy.
Okay, we can certainly do that. You don't want to mess with ui and vy?
Okay. Sure, yeah.
It's like in poker, you want them to pick the odd ones. So you say, pick the odds or the evens. And they say, I want the evens. Okay, throw out the evens. We have the odds. Right, that's a standard thing. Okay, so this is u sub x times h1 plus, instead of u sub y, I'll put, Kayla.
U sub y, you would put negative vx.
Perfect. Negative v sub x h2 plus I times v sub x h1. And then instead of v sub y,
uy.
Exactly. Plus v sub y is imaginary. It's equal to real. H2, right? With a small error term. Now what? What the heck are we supposed to do now? Well, let's try grouping these slightly differently. I have an h1 term and an h1 term. So that's a u sub x plus I v sub x times h1. And I have these two h2 terms. So let's group the h2 terms. I guess I can pull out an I. I'll pull out an I h2, and what's left over? Thomas?
V sub x h2 times negative 1 over I, which is I.
V sub x, I have the v sub x with a minus sign, and I'm pulling out an I.
Yeah, so you have times negative 1 over I.
Negative
so that's
1 over I, also known as plus I.
Exactly, yeah.
Perfect. And what about here?
Oh, just u sub x, h2, I thought, yeah.
Plus little oh. So what's going to happen as h gets smaller and smaller? Is it something that's uniform in h? Is this something that we can divide by h? What just happened? Nick says yes. Rishab, you have a question or you're saying yes? Yeah. Can I pick on Kailash? Can I pick on you?
Yeah. Yeah, you have an h right there, multiplying by the factor of ux plus ivx.
Exactly. So this is just a tiny bit of algebra, and remembering that this thing is h itself. So that's it. That's all we needed to know. Because now f of z plus h minus f of z over h makes perfect sense, right? I took this, divided it by h, makes perfect sense. And what I get is d dx of f plus little o of h. Little o we divided by h. So that's little o of 1. I don't need the absolute values of 1. Little o of 1. In other words, this thing goes to that thing, and that thing is also known as f prime of z. The limit exists, and it's the derivative. So the function is holomorphic. Okay, so it's just a little bit of algebra after the Cauchy-Riemann equations that lets you prove this theorem. Where's the theorem? Anyway, you know what the theorem is. It's the converse theorem. If u and v are real differentiable, it's not enough. Okay, so this is the next thing I'm going to say. It's not enough for the partial derivatives to exist and satisfy the Cauchy-Riemann equations for holomorphicity. But before we get to that, is everyone happy with the converse theorem statement and proof? So far, so good? Okay. Any questions? Sriram, you're going to say something? No. Burchin, it's okay? All right. So, caveat. Let's see. Let's make this red. I'm playing around with my toy. Caveat. It's not enough for the partial derivatives to exist and satisfy Cauchy-Riemann for holomorphicity. Okay, and the standard example is this function, z to the 5th over norm z to the 4th. So the calculations, I want to do this, I want to show you what's really going on. So let's switch to Mathematica, if I can. Okay, can you guys see this? So what I said is my function f is z to the 5th over norm z to the 4th. You guys can see what I'm writing? So there's another way of saying this. What's norm z to the 4th? It's norm z squared squared. And norm z squared is what? So I have z to the 5th over norm z squared is z bar. So this is z squared, z bar squared. And of course I can cancel the z's on top and bottom. It's z cubed over z bar squared. Okay, let's play with this function for a second. So first of all, let's look at it. Complex plot, z to the 5th over norm z to the 4th. As z goes from, I don't know. And you remember what this is going to do? It's going to give us the absolute value, and then it's going to tell us the argument by the coloring. Looks pretty good, right? Nice function, beautiful. Of course, we're going to be suspicious because there's z bars there. So already we know it's not going to be, right, it's not defined at 0, but it makes perfect sense to define it as 0 at 0 because it's perfectly continuous there, going to 0. Okay? So let's make a note. F goes to 0 as z goes to 0. So that's a perfectly fine function to try to analyze. Let's see. If we make z equal to x plus iy and z bar equal to x minus iy and norm z squared will make z times z bar, and maybe we have to simplify. Let's see if that works. Yeah, so it knows what norm z squared is. Good. And then, so our function is z to the 5th over norm z squared, right? That's our function. And we can expand this. Let's see if this works. Okay. And now let's compute the real parts and imaginary parts. So u is equal to real part of f. I have to simplify this. Let's see, full simplify with the assumption that x is an element of the reals and y is an element of the reals. Oh, come on. It doesn't know the imaginary part of 1 over, it's kind of stupid sometimes. Let's try this. Oh, it's having trouble with the fact that it might be 0. Okay, so let's just make it positive. Right, so that's u. This is the real part. This is the calculation I didn't want to do by hand. This is the real part. Okay, little nasty. And of course we can in the same way compute v, which is the imaginary part. And there's the imaginary part. Make sense? Let's compute the partial derivatives. So what is the derivative of u with respect to x? It's this nasty thing. Let's simplify. Okay, so this is ux. Ux is the derivative with respect to x. And what's the limit of ux as x goes to 0? Well, it has a limit. It's some nice thing. How about as y goes to 0? Okay, it also has some nice. It seems like a nice function, right? How about the derivative? Okay, so let's get all these derivatives. The derivative of u with respect to y, the derivative of v with respect to x, and the derivative of v with respect to y. Does everybody see what I'm doing? I'm just letting it compute all these things for me. All right. So what are these limits? The limits always exist. Let's just have a look at them for a second. This is a sextic in x on top and a sextic in x on bottom. And it's also a sextic in y on top and bottom. So it's slightly subtle what it's doing at the origin. But nevertheless, we should be seeing that this thing is does satisfy the Cauchy-Riemann equations. Let's see, limit ux. Let's do limit ux minus vy. Ha, something happened. Let me restart the kernel. Something funny happened. Here's the norm. Did I do anything wrong? We got u, we got v. I claim that this satisfies the Cauchy-Riemann equations. I differentiate with respect to x on u, I differentiate with respect to y on u. I differentiate with respect to x on v, and with respect to y on v. I'm supposed to get all these partials. Let's see, as x and y go to 0, am I getting 0 here? Something's funny. Anybody see what I did wrong?
I don't see anything because I guess as ux goes to 0, you should get 5, and the same as vy goes to 0, you should get 5. Like if you look at what ux and vy outputted.
Yeah, let's look at this. We're saying as we are saying, oh, I see.
Professor,
Yes.
I didn't get it. Like, why would it satisfy the Cauchy-Riemann equations? This function?
That's what we're computing. We're trying to see that it satisfies not in a neighborhood of 0, 0, but at 0, 0.
Okay, okay, okay.
In our proof, we only use that the Cauchy-Riemann equations are satisfied at that point. But we use differentiability. We use the fact that there's a tangent line. So,
to do with the fact that you're doing as y approaches 0, or should that not matter?
well, I'm getting some funny behavior that's confusing me because it's not what I was getting when I. This is the standard example of a function that does satisfy the Cauchy-Riemann equations at that point, but not in a neighborhood at that point. Let me show you what's going on with u. So let's plot u, plot 3D. U as x goes from minus, I don't know, a half to a half, and y goes from minus a half to a half. Okay, so the point is, along the axes, there's nice behavior, and the derivative indeed exists in both directions, and we can plot v also. Let's see, can we plot u and v at the same time? Yes, we can. So all of the functions have nice derivatives, and those nice derivatives agree at the origin, but there's no plane. They're not R2 differentiable. There's no plane that is a good approximation to the value at 0, 0. If you can kind of see, I don't know how easy this is to see or not. Maybe I should leave this as an exercise and move on. Let me zoom way in. Yeah, it looks the same when you zoom in. It doesn't, there's no tangent plane. There's no nice tangent plane. As we zoom in, we always have this oscillatory behavior. But, so, in the interest of time, let's leave this as an exercise. Ux does equal Vy, although I'm not getting that right now. And Uy equals negative Vx, because they're all equal to 0. So all of the partial derivatives, only the partial derivatives, all equal 0 at 0, 0, but not near. Yeah, that's what I want to do. It's not that I want to take a limit. It's that I want to evaluate. That's what I'm doing wrong. I want to evaluate this at x equals 0. And it's still giving me not what I'm expecting. How about
You want x and y as 0?
Well, you see, once I set x to be 0, I should already get 0. The limit should be the same. Okay, so there's some funny thing that happens. If I take the derivative in the mixed direction, then I'm getting a limit. And if I take it in the opposite directions, then I get the opposite limit, it seems. And the same is going to be true with Vy versus Ux. Yeah, so you see these agree. They're like negatives of each other or whatever, because they're both 0. And these are agreeing. So this is the Cauchy-Riemann equations becoming satisfied while the function itself is not holomorphic. All right, this is a good time for a little break while I try to figure out why this isn't doing what I hope it would.
Okay. Oh, sorry.
Sorry, go ahead.
Oh, did you want to go first?
You can go first.
Okay, I was just going to say that I should mention that, or it might be worth mentioning that I think that example does work. It's just the Mathematica that's not working, because if it's the argument squared, if we go along the real axis, then the argument squared on one side is 1 and the argument squared on the other side is 1.
Right.
So it should work, at least in that case.
Right.
But yeah. So my guess, I haven't worked out the other, but my guess is that the example does work, but something's going wrong in Mathematica.
Okay. Well, okay. Exercise, figure out what's going wrong. Let's talk about it. I have more I want to get to, so we could spend when something starts going wrong, especially if it's going wrong in Mathematica, we'll spend the rest of the time finding the bug instead of getting to the material. So let's come back to the example. Okay, so that was a little discussion of Cauchy-Riemann, the converse theorem, which so now we have an if and only if, right, I could put it even here. The opposite direction we already proved, if f is holomorphic, then in particular, it's real differentiable, R2 differentiable. And so it's imaginary parts and real parts are, and satisfy Cauchy-Riemann. And now we know the converse. And the converse is just this bit of algebra here. The Cauchy-Riemann lets you write things in terms of h, so you can divide by h. Okay? All right. Let's talk about analytic functions. So again, recall definition, f is analytic at, I should really say near z in some, so f is always from some open domain to the complexes. F is analytic near z if what? Somebody told us the answer last time. Was it Anna? Did you tell us the answer? No.
I think it was someone else, but it's the Taylor series thing, right?
Yeah. Who said that? I don't see. Oh, Hannah? Hannah, you said that?
Oh yeah, that was me.
Yeah, great. Exactly. If there exists a Taylor series, AN, well, Z0, Z minus Z0 to the N from 0 to infinity, that converges absolutely, and an R, if there exists an R, positive, strictly positive, and a power series which converges absolutely for Z in a ball of radius R about Z0. These balls are always open for me. And converges to the value of f at Z. Okay, so you have some point Z0. There's some positive radius ball. This is a ball of radius R around Z0, so that for every Z in that neighborhood, there's a power series that converges to the value of the function. Okay, so that's analyticity. And I want to discuss connections of analyticity to holomorphicity. We already saw a whole bunch of, so most conveniently, for most of our examples, we'll look at series about the origin. So let's look at some examples. I want to know when these things converge. I want to know some properties about analyticity. And the theorem that I'm trying to get to is that analyticity implies holomorphicity. Okay, so some examples. Here's a power series. Anybody know? So when I write a sum like this, I always mean over the positive, the non-negative integers, the natural numbers. Anybody know what z to the n over n factorial sums to? Yeah, good job making it e, Thomas. Right, so this is xz. And what is the radius of convergence?
Isn't it entire?
Yep. Yeah, so this R could be infinite, less than or equal to infinity. Could be equal to infinity. Okay, great. We know this one. We know, how about z to the 2n over 2n factorial? And let's throw in a -1 to the n for good measure.
Cosine or sine.
Cosine. And again, R is infinite. And as you said, sine. Berchin, which one's sine? It's like the odd.
Yeah, the odd one.
The odd ones is sine. And of course, that gives us formulas for sine and cosine in terms of, so this is e to the iz plus e to the minus iz over 2. And this is e to the iz minus e to the minus iz over 2i. Okay, good. We know all these things. Great. So these all have infinite radius of convergence. How about just z to the n? What does that converge to?
1 over 1 minus z.
Yeah,
Z,
geometric series.
And the disk.
For z less than r equals
1.
1. Okay. So here the ANs, yeah, let's look at what the ANs are. The ANs in all of these examples, at least in absolute value, are like 1 over n factorial, right? In this example, the ANs are all 1.
Geometric also converges on the boundary except at 1.
Yes, yes, that's true for the geometric. In general, it's rather delicate. In fact, you have a homework problem on some examples of how delicate things can be at the at the largest radius of convergence. How about can the ANs be like polynomially growing or even exponentially growing? What if the ANs are like 2 to the n? So now I'm summing 2 to the n, z to the n. Can I sum this? No, the ANs are blowing up too fast, right?
That's just 1 over 1 minus 2z.
Yeah, it's just 1 over 1 minus 2z. The 2 can be grouped with the z, which means z had better be less than a half in absolute value. Okay, so this is my r now. Okay, how about, so the coefficients of a Taylor series can be blowing up exponentially and still have a positive radius of convergence. How about super exponentially? N factorial z to the n. Brandon says no. Why, Brandon?
Ratio or Ruth theorem, whichever one makes sense.
Exactly. Exactly. Wherever z is, there's some n after which, for n bigger than absolute value of z, n factorial z to the n, or maybe a little bit larger than that, is not even, this isn't going to, this is going to infinity. So the terms are not going to 0, and that's a necessary condition for a series to converge. Okay, so terms are not going to 0, so diverges everywhere. Diverges. So r is equal to 0. Except at the origin, except when you plug in 0 for z, that's the only place where that series converges. There's no actual open region for which the series converges. Okay, so I want to understand the general statement. What happens in general? What happens in general? This is a beautiful theorem of Hadamard. Hadamard. I will not try a French accent again, sorry. Hadamard's theorem says, let an z to the n be a power series. There exists some r, which could be 0 and could be infinity, such that, so for all z of absolute value strictly less than r, the series converges absolutely, which of course if r is equal to 0 never happens. And for all z greater than r, the series diverges. And he identifies exactly what r is. And r is 1 over L, where L, does anybody know what I'm about to write? I'm just curious.
It's like a limb soup of something.
Yep, yep. So the question is, what made these, what's the connection between these r's and these ANs? That's the question. So you see, if you blow up like 2 to the n, then the radius of convergence is a half.
It's given by
1 over the radius of convergence is 2.
1 over the nth root, though.
The nth root. It's exactly, this is the key example to explain Hadamard's theorem. It's the nth root, an to the 1 over n. If L is the limb soup, which could be 0 in the case of the exponential function or infinity. In other words, r could be infinity if L is 0. Because you have 1 over n factorial, right? Let's go back to our example of an equals 1 over n factorial. What is the lim sup, which is also the lim, of 1 over n, the nth root of n factorial? Is this something people have seen before, Stirling's formula? How big is n factorial, roughly? Let's not be precise.
N to the n, e to the minus n, root 2 pi n.
Yeah, I'm ignoring constants. So it's like n to the n is the leading term. So if you take the nth root of that, the nth root of n to the n is n, which is blowing up. Okay, so this L in this case is infinity. It's 1 over n factorial. So R is infinity, L is 0. This is going to 0. Does that make sense? So this formula, at least, we haven't proved it yet, but at least it's consistent with the examples that we saw before. If ANs are all 1, then we're good. If ANs are n factorial, then it diverges everywhere. L is infinity, and so R is 0. Does everybody see that? Any questions on this? Okay, so let's prove it. Proof. Let's prove 1, and I think I'll leave 2 as an exercise. Right, so first let me assume R is not 0 and finite. The cases R equals 0 and infinity are exercises in the homework. Assume R is finite. And so again, L is the lim sup of the nth roots of the ANs. And let Z be less than R. Now, what does it mean? What does it mean for this thing, for L to be the lim sup? We have our ANs, right? So here's n versus AN to the 1 over n. So here's L somewhere. L is also some number between 0 and infinity. So the ANs are doing something, and the lim, what does it mean for the lim sup to be L? It means that for all, this is equivalent to, for all epsilon, there exists an n, so that for all n bigger than that n, in other words, for all epsilon, what I'm about to write is that AN to the 1 over n is less than L plus epsilon. So if I go epsilon above L, there will only be finitely many values of this thing above that epsilon. There's some point capital N, so that all the values forever from then on are below L plus epsilon. Right? That's what a lim sup is. Well, so what epsilon do I want to take? R, so Z is strictly less than R. So here's R, and Z is somewhere strictly less than R. So there's some epsilon. How do I want to say this? There's some epsilon so that L plus epsilon times Z. So there exists epsilon such that L plus epsilon times the absolute value of Z, whatever that is still strictly less than R. In fact, less than some R less than R. Okay? So I'm just giving myself a little bit of room. There's some R here, some little r, which is strictly less than big R, and and there's still epsilon of room around that, which I can put into, sorry. What am I trying to say? I'm trying to say that, that R, Okay, I have this. And R is 1 over L, right? So LZ is less than 1. And now I can take, let epsilon, so that's all I want. And now let epsilon be small enough that not only is L times Z less than 1, but L plus epsilon times Z is less than some R strictly less than 1. I'm using the fact that I have room in the real numbers. Okay, LZ is some number less than 1. Here's 0, here's 1. L times Z is some number that's less than 1 by the assumption that Z is strictly less than R, and R is 1 over L. Are you guys following? Now we're really starting actual analysis. Before we were just playing around. So now we're doing serious, somewhat more serious stuff. I have room here to make L a little bit bigger. So L plus epsilon times Z is still less than 1, which means it's less than some R less than 1. So I can sneak things in between. Okay? And now let's look at the tail of the series. So look at the tail, n greater than capital N. So we fixed epsilon. That gives us a capital N. So look at the tail. Of course, the first finitely many terms are finite. We want to know, does this series converge or not? And let's see if it converges absolutely. So I have an absolute value of z to the n. Right? The ANs, after this point, the ANs are less, than L plus epsilon to the n. The ANs can be replaced by L plus epsilon to the n. And the z is where it is. And this, by construction, is less than R to the n. And R is strictly less than 1, so this converges. Okay, so the tails are indeed finite for any z strictly less than R. Any questions? So again, what are we trying to prove? We're trying to prove, step part 1 here, is that if z is less than R, then the series converges absolutely. We look at the tail of the series, and we look at its absolute value. N is some fixed number. The sum for the first n values can be whatever it wants to be, but the tail does not blow up. The tail is bounded by R to the n. R is strictly less than 1, so this is less than the geometric sum. Okay, and the bit of analysis is if z is less than big R, then LZ is less than 1, which means L plus epsilon z is less than some number less than 1. And that's it. This is true for any z less than R. So we're done. Okay, in the interest of time, let me not do part 2, but let me make it an extra exercise. I don't think Stein-Cekarchi don't have this as an exercise. So added exercise to be handed in. To be handed in with your next homework. So exercise. Test your understanding of this proof by proving part 2. How do I do this? There we go. That's kind of fun. Okay. Prove part 2, meaning if z really is bigger than R, then the series must diverge. What do you think you're going to do? You're going to do a similar kind of argument, except you're going to make R bigger than 1, and the sum of things bigger than 1 to the nth power diverges. Okay, so this is a good test of have you followed all of the intricacies of this proof that we just discussed. Any questions so far? Yeah. What can I do in 5 minutes? Well, let me state a theorem. Let me state a theorem, and I'm not sure we're going to be able to prove it, but at least we'll start thinking about it, and we'll prove it next time. So here's the main theorem. Theorem. Analytic implies holomorphic. So if f is given by a power series, let's make everything around z naught equals 0 so that I don't have extra crap to write, has r bigger than 0, then f is holomorphic on z less than r. Can you see that? A little sloppy. If you can't see my writing, please ask me to correct it. I'm not sure that's much better. Okay, analytic functions are holomorphic. It'll be quite a bit more work to prove, not that much more, to prove the converse, but this we can already prove immediately. I mean, we're kind of talking about this in the informal chat before. Really, the thing that makes complex analysis so amazing is that holomorphic functions are analytic. And then we're really just doing the theory of real analytic functions. It seems kind of funny just to study real analytic functions. It seems like a very niche thing to do. You should study all real differentiable functions if you're going to, and that's what you're doing in your real class. But really the miracle is that holomorphic functions are analytic, and analytic functions are the ones that have all these amazing properties. Infinite differentiability and all of the, every integral is 0 and so on. And they satisfy, they're not just analytic, they also satisfy the criterion. Okay. Let's start the proof and we'll see how far we get. Maybe I'll give you the flavor of the proof and then I'll fill in the details after. So it's holomorphic, and there's more, and moreover, and the derivative is given by a series a to the n. I mean, you just differentiate term by term, which has the same radius r of absolute convergence. So you took, in other words, the new ANs, AN prime, the ANs of F prime are n times, let's see, I guess it's n plus 1 times AN plus 1 or something. I mean, if I rename this n plus 1, n to n plus 1. Okay, why is this true? Let me see, so key steps, key ideas. All right, we know that F is analytic. So let Sn of Z be the partial sum up to capital N of ANZN, and En is the rest, n bigger than n, ANZN. I claim, well, I'm trying to claim that the derivative will be equal to this series. So let G be the series, G of Z be this series. Why does this have the same radius of convergence? That's the easiest thing to prove. What's the limit of n to the 1 over n as n goes to infinity? Yeah. Yes, some people see it immediately. If you don't see it immediately, then you make this equal to L and take log L. And log L is 1 over n times log n. You have a log on top and n on bottom. It's easy to see that goes to 0, so L goes to 1. So adding an extra factor of n doesn't do anything. That's why polynomials, changing things by polynomials doesn't do anything. It's only when the ANs are exponentially large that you start changing the radius of convergence. Okay, so this has absolute convergence for z less than r. Okay? And what I want to say is that f of z plus h minus f of z over h is close to g of z. So my claim, what I want is to show that this difference goes to 0. That would mean f is indeed differentiable and g is indeed its derivative. And the key steps, the details of which we'll work out next time, is it's commonly referred to as a 3 epsilon argument. 3 epsilon argument. So the point is, first of all, f of z is Sn plus En, the initial sum plus the error. And so when you stick that in for f, what you get here is you get Sn of z plus h minus Sn of z over h. And now I'm going to add and subtract Sn prime. So this thing is less than, I'm going to add and subtract Sn prime minus g. And then the last thing is En of z plus h minus En of z over h. Okay, so we'll make this less than epsilon. Why is that less than epsilon? I'm giving you a crash version of this proof. Why is this thing less than epsilon? What's Sn? We'll do all of this again on Tuesday. I realize I'm going fast. Sn is a polynomial. Polynomials are holomorphic. That doesn't take any, that's not difficult to see. So these are holomorphic and this is their derivative. So there's no problem making this small. How about this? Why is this small?
Convergence.
G is a convergent power series, and Sn prime, we can differentiate term by term. Sn prime is the thing that G converges to. So this is small. So they're all small for different reasons. And why is the last one small? Well, it's an error term. You do have to worry about this over h. You have to do a little bit of work to get this over h, but it's an error term that converges absolutely. So this will also be less than epsilon. And that's the 3 epsilons. All right, we're out of time for today. We're going to start with this theorem on Tuesday and get to work on it. And I think that's it.